Good morning, everybody, and welcome to our Winter 2021 Saturday Morning Physics Series and today's live lecture by Dr. Maria Elidaiana. I'm Physics Professor Tim Chupp, and I'm organizing this winter's lecture series with Professor Roy Clark. We want to thank you for your support of Saturday Morning Physics, joining us for these online lectures, and looking forward to your support of Saturday Morning Physics, joining us in person hopefully next fall with bagels and coffee and science. If you would like to explore financial support for our program, please go to our website or search UMich Saturday Morning Physics. I want to let everyone know that after the lecture, Dr. Elidaiana will answer your questions that you submit during the lecture or discussion. Please email your questions to physics@umich.edu. We're looking forward to hearing from you. Today, it's my great pleasure to introduce Dr. Maria Elidaiana, who is a postdoctoral research fellow here at the University of Michigan and a member of the Dark Energy Survey, which she will tell us about today. Her research focuses on observational cosmology, gravitational lensing, gravity clusters, and gravitational waves. Maria grew up in Brazil and did her undergraduate work from the Rio de Janeiro State University, completing her Bachelor of Science and Bachelor of Education degrees in physics. She then moved to graduate study at the Brazilian Center for Research in Physics in Rio, working on using starlight to measure the masses of galaxies. Maria completed the Master of Science degree and her PhD in 2017, and then she came to the University of Michigan last fall after 2 years at Brandeis University. She's been in her apartment ever since arriving in the fall. Maria is a member of the American Physical Society, the LSST, Dark Energy Survey Collaboration, the Cosmic Explorer Consortium, and the SNOMAS 2021 Early Career Survey Initiative. She's also a University of Michigan Museum of Natural History Science Communication Fellow. Thank you, Maria, for kicking off this winter Saturday Morning Physics series, and we're really looking forward to your lecture. Maria.
Thank you, Tim. It's my pleasure to be here, and good morning for everybody who's listened to me. So today, I will talk about these giants in the sky that are the galaxy clusters. As you can see from my spoiler image here, where you have different same galaxy clusters, but one thing we can do with them is to count them and weigh in them. But the problem is galaxy clusters, they are on the sky. We cannot touch them. Then how can we measure the mass or weigh in those objects? And that's what we are learning today. So my talk is divided in four main sections. First, I will give an introduction about my research area, which is cosmology. Then I will talk a bit more about the galaxy clusters, how can we weigh them? And for this, we will be using the gravitational lensing effect that I will explain. And why do we need to count them to understand better the universe? And this is just a nice image from the Dark Energy Survey where some of my colleagues made some art for it. Okay, so I think one of the questions that some people may once have thinking about is, where did you came from? And this is a very, very difficult question. If you come back in the years, in the societies from different cultures, many people have different explanations to explain the universe that is around us. And here I have just some representations of different cultures and how they explain the universe they see. And here, just to show to you, this is what we call a nebula disk, and this was found in Germany, and it was produced 2,000 years ago. And this is a representation of the sun and the moon and some stars. And then some years later, in the ancient Egypt, we start to have this representation of gods and goddess that represent the natural process that they see, like the sunrise and sunset. We have a goddess here representing the sky and another one representing the earth. And this keep going, this kind of explanations about the universe. We have in the ancient China, we have this model here where this circle is the sky, this disk here is the sky, and this square is the earth. At that time, they thought the earth was flat. So, and more recently, in the 17th century, we have a representation here where we have the sun as the center of our universe. Another interesting interpretation about this question, where it came from, what we have around us, it's from this representation from some native people in South America, where we have the sun and the moon, and they are twin gods, and each one is responsible for different features in the features and patterns on the nature. Like in this, on the left here, you see things more like open lines that you can identify in the nature, and in this other one, you have these closed shapes that is associated to the moon. So there are many more other representations of the origin of the universe. It's a very interesting topic if you want to look more and learn more. But what happened is that at some point we start to have the development of devices and some in the telescopes and all kinds of scientific devices that help us to understand better what's going on out there. And by using these telescopes and look even further in the sky, we start to collect the light and put together the data and try to understand better by observing and making theories and testing these theories of how the universe works. And here is just a summary image that shows the current model that we have for the universe. Basically, this model explains how the things start and how the universe evolved. And I will not go into the details of each one of these phases because there is a previous lecture. You can search, for example, a lecture from Professor Dragan-Hutter, who explained well this model for us, so you can have a look at that video. But I will just bring you to attention to important phases here in this model. The first one is the very beginning that we call the Big Bang. This is a name to, this was not explosion, as you might know, but it was the beginning of the universe not in a point, but it was the beginning of everything, space and time. And you cannot say anything because you cannot probe or look with observation to that time, t = 0. So you just have assumptions or models for the time. But a fraction of seconds after the Big Bang, we start to have information about how the universe works. Because although it was very dense and with high temperatures, a very small region, the universe starts to expand. And when they start to expand, it was very fast, this phase of expansion, and we call this phase as inflation. And in that phase, we have the seeds, like the small fluctuations that gave origin to the bigger and bigger structures that we see now in the universe. So, but at the time, the region and the space was so dense that even the light could not pass through the matter. Only 380 years after the Big Bang, the light starts to separate from the matter. And then you have the first, what we call the first light of the universe, which is a remain light from this beginning of our universe. and that we call the cosmic microwave background. So, and then after 20 millions of years after the Big Bang, we start to have the formation of the first stars and the first galaxies. And that's a very important phase in the universe, because there we just have, galaxy clusters, matter evolving with the gravity up to the time that we are right now, circa 13 billion years after the Big Bang. And we can see here the universe today is formed by galaxy clusters. And you can think galaxy is a collection of stars. And galaxy cluster is a collection of galaxies, as you can see here in this picture. And we just live in one of these not special galaxy, in a galaxy cluster that we call the Milky Way. And we are here just in one arm of this galaxy or solar system is there. And we are the third planet orbiting the one star that we call the sun. So this is just a brief history of the universe, and this just represents the best model that we have so far based on the observations that you have from the universe that represents our knowledge of how the universe began and how it evolved. So this is what cosmology does. It's to study the origin, the composition, structure, and evolution of the things in the universe. And this model that I just mentioned to you is called lambda CDM, but you just can talk this as the Big Bang model if you want. And it's the standard model of the cosmology today. That means that most people accept that. But there are other models, but I will not talk about those today. One good thing about the lambda CDM and what made this model, the concordance model, is that it can not only explain the observation that you have, but also can make predictions that can be tested. And this is shown in this video, where we have two different universes, two different simulations of universe. On the left, you have the lambda CDM, and on the right, we have another universe. And as you can see, the structures here, this is basically particles evolving in a box that become bigger structures like galaxy and galaxy clusters. And as you can see, there is a slightly difference on how these the matter here in each one of these universe evolve and agglomerates together. So that's the importance of having a model that gives some prediction on how the matter will evolve. And then we can look to observations and see if our model fits one or the other universe. By the way, the universe on the right was discarded because it do not fit the observation that we have. Another important point about the universe is to understand the content that we have today. And there are basically three components of the universe today. The first one is what we call the conventional matter. This is the stuff that I am made of, you are made of, stars and galaxies are made of. Everything that you know, it's made of this conventional matter. But this is only 5% of the content of the universe, of the total content. Most of the matter is in the form of some mysterious, kind of invisible matter that we call dark matter. But how do we know, if you cannot see, how do you know this dark matter exists? We know because we look to the movements of stars in galaxies, or the movement of galaxy and galaxy clusters. And from these observations, we see that we need to have more matter in those objects to explain the movements that we see. And that's why we say that we need dark matter. And if you know that what dark matter is, you will certainly win a Nobel Prize, because no physicists know yet what dark matter is. And from the previous slide, I just mentioned to you that we have this evolution of galaxy and galaxy clusters with gravity over the time. But this is just half of the history. We would expect that at some point, the gravity will win this expansion of the universe and things will start to get together. But what we see with the observations that this is not happening. What's happening is that the galaxies are moving away from each other. That would mean that we need a force that's different from gravity that puts things together. It's putting the things far away from each other. So it's a repulsive force. And we name this kind of force dark energy. We also have no idea what dark energy is. But as I say, from the observations, we know that it must be there. We just don't know exactly what it is. And this is, again, is a Nobel Prize question. If you know, you get a Nobel Prize. So basically, this is the content of the universe. Dark energy and dark matter made more than 95% of the content of the universe. And you have no idea what they are. But one thing that we can try to do is try to answer these questions and make questions to try to get closer to the answer of what is dark energy, is really responsible for the accelerated expansion of the universe, what's dark matter, what's the properties of dark matter. And as a physicist, we create models. And the good thing about models is that we have parameters that we can measure. Parameters are like quantities that if you move or change a bit the value, we will have different universe. And in this case here, there are two main parameters in cosmology that we are trying to measuring today. The first one is the rate of the expansion of the universe that we call the Hubble parameter, or H0. And here in this plot, I have several measurements for this parameter. But as you can see here, we have two bridges. This first bridge represents the measurements that we get from the early universe. And this other bridge, there are the measurements that we have from the late universe, from today, right? And as you can see, there is a gap. Those measurements do not match. So what's going on there? That's a question that physicists and cosmologists are doing right now and trying to answer. Another parameter that we have interest is what we call the S8. You don't need to understand what S8 is, but you just need to understand the effect that this parameter has in your model of the universe. Basically, this parameter gives us some idea on how the matter get together, how the structures grow together to bigger and bigger structures. And here in this plot, we have two different values of SH for two different universes. If you have a low value of SH, like 0.8, we have this configuration here. These red, yellowish dots here are the largest structure that you see in the universe, the galaxy clusters, for example. But if you have a value of S8 that's higher, in this case 1.3, as you can see, we have even bigger galaxy clusters are formed here. And we have more regions where we have less matter, these blue regions here. So if you compare those two images of this different universe, you can say that this one on the right is less homogeneous than the one on the left. And that by measuring this value of SA8, we can determine from observations and compare with these two predictions to see which one is the right one. And as I will explain later, this parameter S8, it's really related to the number of clusters that we see in the sky. So here it's just a summary of the different measurements from the S8 quantity that we have, made from different surveys, different astronomical projects that look to the sky and measure this quantity in different ways. But basically, just have to pay attention here that all these points here are measurements of the late universe. Only the magenta ones are the measurements from the early universe, from the CMB. And as you can see, it looks like the late late time measurements seems to be a bit lower than the value from the CMB. If this is true, if those measurements are different from from the late universe, it might mean that we have some new physics that we do not understand, and we need to find out to understand our universe. But I don't want to be the boring person here, but it's probably more likely that we are not measuring well those quantities. But in the language of physics, we say that probably those measurements are facing some kind of systematic. So, but I will explain what is this systematic errors that I just mentioned. So when you go to the lab and you do any kind of measurements, you have an average value and you have an error in your estimate of that value. And there are two sources of errors. The first one is what we call statistical error. And this is a random error that happens by chance. And as you can see here in this diagram, these are different measurements that, because something happened while you are doing your measurement, something random, you have different measurements every time that you do your measurement. So this is a random error. But what you can do to remove, or at least to take into account this statistical error, is to measure your quantity more and more. That means you have more and more samples to perform your measurements. So when you increase the number of samples that you measure, then you start to still have some spread around, but you start to get closer to the center of this picture. So to solve problems with statistical error, you just have to do more measurements. But the other kind of error that we call systematic is the error that is not random. It's something related to the design of your experiment, the collection of your data, some wrong assumption that you have in your analysis. And this you cannot eliminate, but the only thing that you can do is to correct. And here's the representation of a systematic error. So we know the true value must be here in the center of this figure, but you measure then with a low scatter, but far away from the true value that we should have. So what cosmologists and physicists want to do is try to understand all the possible kind of things that have influence in your measurements that make your measurements go far away from the truth. So we try to bring those points here to the center to get as close as possible from the true value that we have. So that's why systematic errors are very important for cosmology. Okay, now we can talk a bit more about the galaxy clusters, the properties of the galaxy clusters. They are big, of course. They have 10 to the 14 solar mass, and they have a size of 2 to 10 megaparsecs. Okay, these are weird units, but I put here in the metric system, one solar mass is around 10 to the 13 kilograms. That means 1 followed by 30 zeros. And 1 megaparsec is of the order of 10 to the 22. This is 1 followed by 22 zeros. So I have no idea how big it is. I just know it's big, but I cannot imagine how big it is. But if that makes sense for you, one solar mass has the same mass of 333,000 Earths. And this megaparsec unit is equivalent to you go to the center of the Earth and walk around 100 trillion of times around the Earth. So yeah, it's a large distance, right? So, but this is just about the dimensions of the galaxy clusters. They are formed mostly by red galaxies, as you can see here in this picture. Most of the points here are kind of reddish. And those are elliptical galaxies. They are galaxies that are not forming stars anymore. And there is also extremely hot gas inside the galaxy cluster. But this is all visible matter. Okay, you can see the stars, the gas we can detect in different ways, but the majority of the matter in a galaxy clusters, 8% of the matter of the galaxy cluster is made of dark matter. So that matter that we cannot detect with our devices or telescopes or detectors. Because this is a very extreme environment with, gas, stars, dark matter, gravity, all evolving together, the galaxy clusters are very important to study astrophysics, different process, but they are also important for cosmology. As I mentioned to you, then if I know the number of galaxy clusters that we have in the sky, we can infer a value for that parameter as 8. And that's why it's important to count, not only measure the mass, but count those galaxy clusters. But the first thing, when we look to the sky, we just see a bunch of galaxies. How can we then identify a galaxy cluster? There are two ways that we can do that. The first one, we can, as I just mentioned, most of the galaxy cluster is made of red galaxies. So if I look to the sky and see an agglomeration of red galaxies, it's most likely that I'm looking to a galaxy cluster. So this is one way to identify galaxy clusters in the sky. Another way is not take into account the color, but just look to all the density of galaxies in the sky, in the plane, like here, and try to find these regions here where we have some overdensities of galaxies. And these would be all galaxy clusters. There are different techniques to try to find out these overdensities. And in this case here is just a mathematical technique called the Voronoi tessellation. So, but just look to the sky, see an overdensity of points or of galaxies, then it's a galaxy cluster. Another thing that is very important is to get the distance to those galaxy clusters. And the distance in this for galaxy clusters is what we call the redshift. And this concept of redshift is very close to another concept in physics that is named the Doppler effect. And if you have seen the Big Bang Theory, I guess you should know what it is. But if you don't remember, I will just play a bit this video.
Hey, Sheldon, there's something I want to talk to you about before we go to the party.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
If I have to, I can demonstrate. Meow.
I hate what Sheldon's supposed to be.
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys,
See? People get it.
See, you get it, right? Okay, let's try to wrap up this information. So he said that the Doppler effect is the change in the frequency between a source who is moving from an observer. But if you can look here, this is the example he did of pretending to be an ambulance, right? That goes closer to someone. When this ambulance go in all direction, that means that the frequency of the sound that you hear, the frequency it's higher. In consequence, the wavelength of this sound wave it is smaller, as you can see here. Lambda is the wavelength of this wave. And then we can here we hear a higher pitch. But if the ambulance is moving away from us, the frequency is lower, and then we have a higher wavelength. So the wavelength increase. This is true for sound waves, but it's also true for luminous waves. Like, for example, here we have some luminous source that is going towards Earth. And then what we see is that the light of that object go to the region of the spectra that is more blue. And if the source is moving far away from us, it means that the light of that source is going to the red region of the spectrum. And as you can see, the difference is the size of the wavelength, right? And by measuring how much the wavelength change from what you measure, for example, in the lab, we can determine how distant this object is. So that's how we get this Doppler effect, this deviation, this shift, this Doppler shift. But for cosmology, for galaxies and objects that are moving away from each other, the cause of the shift in the frequency is not the movement itself. The galaxies are there, just stop at the space. But the space itself, it's moving, it's expanding. The universe itself is expanding. And that's what caused this change in the frequency of the wave.
Hey, Sheldon, there's something I want to talk to you about before we go to the party.
So I just show another experiment that show this change in the wavelength of the wave. That's due to the expansion of the universe.
This is a demonstration used to explain the redshift due to cosmic expansion. We have a vacuum cleaner that's going to be pumping air into a balloon, and on the balloon we have painted a sine wave that we are going to see grow as the balloon itself grows. This is equivalent to what happens to light as it stretches due to the cosmic expansion.
So yeah, that is just a demonstration of what we call the cosmological redshift. That's the kind of redshift that we measure for galaxy and galaxy clusters. But the only thing that we can get from a galaxy is the light. So how do we measure the redshift, right? This change in the wavelength. So what happens that when we take the light, we can decompose that light in a spectra, and as you can see here in this picture. And the important thing is that the spectra has emission and absorption lines from characteristic elements that we have in nature. And we know the position of these lines, these spectral lines, in the lab here on Earth. We can measure that. And then as the galaxies move this away from us, this line will move to the red part of the spectra. And by measuring the difference from what we measure here, the wavelength that we measure here in the lab, with the wavelength that we measure when the galaxy is moving away from us, this difference just made us possible to compute this quantity that we call Z here. And this quantity Z is what we call the redshift. So we are at redshift 0 here at Earth in the lab, and it goes to redshift 1. We are looking to more distant objects, redshift 1, 2, 3. So that's a measurement of the distance. And that's how we get, if you get the redshift for galaxy, we of course can also get the redshift for galaxy clusters. But this technique of get the spectra of the galaxies that we see in the sky, it's very expensive because we need to put a special device that we call optical fiber to get the light for a long time of that galaxy. And there is a limitation in your telescope. You cannot plug infinite number of fibers there to get the light for each galaxy that you see. So therefore, this technique, although it's very precise, it's very expensive, and we would just be able to get few redshifts, so few distance. The way that astronomers find to go around this is to create this technique that's called photometric redshift. In this technique, instead of getting the light, what you do is use different filters represented by these curves here. Each one of these curves here is a different filter that can measure the light at different wavelengths here. So as many, we need to have a lot of filters to be able to cover the entire wavelength range. But as you can see here, with this red curve representing a spectra of galaxies that are moving away from us, so it's being redshift, you can see the absorption and emission lights will fall at different filters. So we want to keep all this information where these lines are. That's why you need different filters. And then again, we have some model of how this spectra should be for different filters. And then we compare the observation that we have with this model, and we get the estimate of the distance. So we get the Z. This technique, with this technique, we can have many galaxies, many galaxies, and it's less precise because you're not getting all the light of the objects in the sky, but it's much more cheaper. So that's what astronomers use to measure the distance up to galaxies and galaxy clusters. Okay, now let's summarize. We know what galaxy clusters are. We know how to measure the distance up to them. Now we need to weigh them. So how do we weigh a galaxy cluster if you cannot touch them, right? So, and the answer to this question is here in this figure. This represents what we call the gravitational lensing effect. So basically the idea behind this is that we as observers here at Earth point our telescopes to a very distant galaxy in the sky. And if there was nothing between us and this galaxy, the light of that galaxy will arrive to us just like as a straight line, right? But we can put a galaxy cluster here. And what happens is, because of the strong gravitational field of this galaxy cluster, the light of that background galaxy is deflected. And as a consequence of this deflection, what we see in the telescopes is, as shown here, is these arcs that we call the gravitational arcs. So basically, this is the image of this background galaxy distorted. And because in this case we have Earth, the galaxy cluster, it also could be a very massive galaxy, and the background galaxies, they are aligned, we have this strong effect. Then we call this strong lensing. But this is very rare, and what you measure most is not this kind of effect, but it's just a slight light change, very tiny change in the shape of the background galaxy. We cannot see in the telescopes by eye this change. What you can do is measure measure a lot of shapes to get some signal of this lensing effect. And this is represented here. What you have, random background galaxy, and then we put a lens, galaxy cluster in the front of it, and we have some slightly change in the shape of this background galaxy. Here is very exaggerated, but we cannot see by eye. We need to measure statistically. One way that you can play around with the gravitational lensing effect is just showing here. You can get wine of glass, and if you look to the bottom part of it, and you pass this glass for some image of galaxies and stars, you can see that how distorted that objects are here. So instead of being like a circle, they become more elliptical. And this is just same thing. The same thing happened in the sky. And what it's very important about the gravitational lensing is that it's not sensitive to just the matter that we see, the galaxy cluster members, but it's also sensitive to the dark matter inside the galaxy cluster. So as you can see here, we have in this GIF a representation of background galaxies, and if there are no clusters, they just follow this blue line here. But then we put a cluster that is also formed by some dark matter, so this more gray halo around this galaxy. And what happens is that the light is deflected, and as a consequence, what we see in the image is this distortion of the background galaxy. And as more massive is your galaxy cluster, more lensing, you have more distortion. So by measuring the distortion, we can then infer how was the mass of the galaxy cluster that was in the foreground of those background galaxies. And basically that's the mystery. That's how we use the light of background galaxies to get estimate mass for the galaxy clusters. One funny thing, or maybe a curiosity, is that the gravitational lensing effect was confirmed in a solar eclipse in 1990 in two places. There was one experiment in Africa, but also they sent some other experiment to Brazil, to this small city called Sobral, which, by the way, is very close where I was born in Brazil. So just saying. And at that time, there was this big debate on what should be the value of the deflection angle of the light due to the gravitational lensing effect. So the Newtonian prediction has a value, and the general relativity from Einstein have another value that is basically the double of the prediction from the Newtonian mechanics. And with this experiment, we were able to measure this deflection angle. I'm not sure if you can see here, but there are some lines here showing the position of the stars behind the sun. And then afterwards, you can measure the same position without the sun being there. And then you made the difference, then you get the deflection angle. So they did that, and they proved that the value from the general relativity from Einstein was the right one. So it's very interesting that this was confirmed in this experiment in Brazil. And basically, these were the start of the gravitational lensing as a research field. And I am proud that Brazil could make part of this contribution to the advance of science. Okay, so now that we know how to identify the clusters, how to measure the distance to them, how to measure the mass, we can finally get cosmology, right? Because to get the cosmology, we have a prediction of the number of clusters of a given mass that you will see in a given distance. And we call this prediction number counts of clusters. And this quantity is proportional, number counts n is proportional to the S8 cosmological parameter. So if you can measure and determine the number counts of clusters and compare with our model, we can determine the value of S8. But one difficult task to measure one of these steps here, which is the mass of the clusters, is that we cannot assess the true mass of the clusters. What we can do is just approximation. As I say, we can use the gravitational lensing to have some idea of the total matter. But we also need some kind of observable quantity that can give us some indication on how massive the galaxy cluster is, because you need to put, as I say, you need to a lot of galaxy clusters to measure the weak lensing effect. So we need to group them together, clusters which are more or less the same mass and that are more or less at the same distance. And one way that you can do this is to look, for example, for the number of red galaxies in the clusters. This quantity we call richness. So if a galaxy cluster have more red galaxies, it's a more rich, consequently a more massive cluster. We can also look to the X-ray luminosity, the luminosity of the gas, and also the stellar content of the galaxy cluster. And at the end of the day, what we want to do is kind of create this relation between our observable, that's the richness or the luminosity of the stellar mass, as a function of the weak lensing mass. And we expect this relation to follow this nice line here. This would be the ideal world, so no uncertainties. But we perform measurements. Therefore, we have uncertainties and we have this kind of scatter. Also, our detectors or telescopes, they have limitations. We cannot observe the very faint galaxy clusters. At some point, we cannot see more the light of faint clusters. And therefore, we have some kind of cut here in the sample of galaxy clusters that we can identify. And then at the end of the day, this is the kind of relation that we call a calibration of the mass from the galaxy cluster that we need to do. And as I will show later, this is most likely the source, is the step that it is more likely that we are doing something wrong. We are facing some kind of systematic error that we are not taking into account. So to identify the galaxy clusters, measure the mass, do this calibration, and get the cosmology, we need to use data. And as I mentioned to you, there are different surveys who are doing this. I am part of the Dark Energy Survey, what we call the DS for short. And basically, this was an astronomical project that imaged the sky in the southern sky. We image this region here, and the objectives of the DS is to measure the expansion of the universe, and by analyzing the largest scale structure of the universe. The survey used different methodologies to do that, different measurements. We use supernova, gravitational lensing, more recently gravitational waves too. But this is just to see that there are different probes to measure the same quantity. So, and the region is about 5,000 square degrees that we image with a camera that has 500 megapixels. And we use 5 filters to get the redshift, the photometric redshift that I mentioned to you. And you have around 100 million galaxies right now. For this project will run for six years. We now just are analyzing the data for the 30 year of the observation, and you have 100 millions. By the end, we will have around 500 millions of galaxies to analyze. And it's just to show a picture that I have the chance to go there and observe for the gas. So that was very fun. But once we observe those galaxies with gas, what you can do now is to measure the mass of those clusters. And for the first year of data of the gas, even smaller area than the total area that I just showed to you, we have around 60,000 clusters that we identify by using that technique of looking to the red galaxies in the sky. We then define the richness, the number of red galaxies as the observable quantity. And then we group the galaxy, all these 60,000 galaxy clusters that has more or less the same redshift and more or less the same richness. And then we measure the weak lensing mass. And here are the result of this calibration that we have. Here is the weak lensing mass as a function of the richness. And the DS result is this blue one. And this area just represent the error bars that we have in our measurements. So you can see DS has very precise measurements for the mass in comparison to previous measurements of galaxy clusters. And another thing that it is important to know here is that now you know for each cluster that you know the richness, you'll be able to find out what's the mass of this cluster. And finally, once we know the mass, we can have a prediction of how many clusters we expect to see of a given mass in a given distance, the number count that I just mentioned. And this, again, is proportional to S8. Here is just a plot, very similar to the very first one that I showed. And this shows the results for cosmology from DS year 1 data. And our results are this vertical white line here, dashed white line. And with the arrows represented here by this gray line, gray region here. But as you can see again, the value of S8 that we have is pretty low. It's very low in comparison to other measurements from other surveys, and even more here from the measurements from the CMB in green here. So what's going on there? Did you find out new physics, or is this a very exciting result? Again, don't go too fast. It's in the article that we describe this result. There is a lot of tests that we did to try to find out if this value here is really true. If this value is true, that would mean that the matter agglomerates even less than the predicted by the lambda CDM. That's the model that currently we accept as the best model to describe the universe. But our result is in tension with that prediction. And we think that, okay, calm down. It must be something that we are not considering in your measurements. And therefore, we believe that this tension between the value that we have right now and the values from the early universe is due to some kind of systematic error that we did not take into account in your measurements. And that's what we are working right now. We are trying to understand what kind of systematic would be responsible to make our value be too low in comparison to the other measurements that we have right now. But it's a hard work, so we need to need many people looking to different aspects of the estimation of the mass, identification of the clusters, to try to find out what's wrong, what we did wrong. So this is still an open question, and try to find out what's wrong with those measurements. I mentioned systematics. I'm the crazy lady for the systematics, sorry. But in the context of galaxy clusters, there are a bunch of them. I will not talk about all of them. I will just mention here 3 of them, so you can have some idea of what could go wrong when you do these measurements with galaxy clusters. So the first one, if you look in this picture, we have here a representation of a galaxy cluster and the galaxy members of this cluster. But as I mentioned to you, we have uncertainties in the estimation of the distance of the galaxies. And what could happen is that instead of saying that this galaxy is here and it make part of the galaxy cluster, we let this galaxy leak to the background sample. So the galaxies that are behind the cluster. But what happens that these galaxies do not suffer from the lensing effect, right? So that means that they will dilute or decrease the lensing signal. So this is a kind of contamination. And it happens because, as I say, we use photometric redshifts, and that might be one cause of that. What we need to do is to find out how much we have to boost the lensing signal that you have, to increase the signal to the level that we are confident that we are reproducing the lensing signal that we would expect for that cluster. Another systematic is related to the shape, to the measurements of the shape of the background sources here, the background galaxy, the galaxy behind the cluster. So the thing is that in the true world, we would have this nice galaxy here and measure the shape. But there is gravitational lensing, so the shape is changed a bit. And besides that, we observe this galaxy in a telescope here on Earth. So we have the atmosphere. And what the atmosphere causes is a kind of blurring of the image. Besides that, we use detectors, use cameras, right? So then we have pixels. We have the image in pixels. And as this is not enough, we have noise to the image. So at the end of the day, this is the kind of image that we have to recover the shape of the background galaxy. And as you may see, like, there is a lot of chance that we are doing something wrong with some of the measurements of this, the shape of these background galaxies. So this is another source of possible systematic in our measurements. And another thing that we don't have a visualization here, but it's very simple, is just the fact that we can give a wrong center for our cluster. We know that there are some clusters, they are colliding, right? And they have a dark matter center from this collision cluster. They have a dark matter center that is different from the center that we usually give to the cluster, which is the brightest galaxy in that cluster. So the brightest galaxy could be that it's not following the dark matter center. So in this case, we say that there are a miscentering of our galaxy clusters. And this will make our weak lensing signal also decrease. So we need to find a correction for this miscentering of the galaxy clusters. And as I say, there are other effects that I'm not talking here, just for the sake of time. It's just to you to have some idea of the kind of things that could go wrong when measuring the mass of galaxy clusters. And we are working on that. We know these corrections, but the problem, this is not a problem. The problem is the corrections that we don't know, right? The corrections that we need to understand better the properties of clusters and apply these corrections. And we are doing this for the third year of the data in YES. And just as a comparison here, for year 1, we have around 60,000 clusters. For year 3, we will have around 20,000 clusters to perform all measurements. And at the first year, what they say is that first we determine the mass and then use this information together with the counts of the clusters to get cosmology. But we see there's something wrong with this approach. And now for Y3, what we will be doing is, instead of determining the mass, we are not doing that. We are just it's like as you let the mass as a free parameter in your model, we just use it. You just use the lensing signal together with the counts. So in only one step, it's like we put all the parameters and vary them all together to try to get our cosmology. And that's the main difference between what we are doing now and what we did before. And of course, we are also looking to different ways that we can get cosmology with clusters, but this is it's subject for another talk. But basically, we are trying to find how to get cosmology in 2 other different ways to compare with the way that we are doing right now, and see if with this 3 different approaches we can get consistency between the cosmological parameters that we have from clusters. Okay, I think that was a lot of information. I hope you can have learned something from that. But if you don't, I just have a summary here that you might be interested in. And basically, what you saw today, what you learned. First, we learned what are galaxy clusters, what they are made of. They have dark matter, they have gas, they have stars and galaxies. And we know how to identify galaxy clusters. We just need to look to the red galaxies in the sky that are close to each other. Then we can measure the distance to galaxy clusters by measuring this quantity that is the redshift. And finally, we can use the gravitational lensing effect to have an estimation of the mass. So we use the light of background galaxies to infer the mass of the foreground galaxy cluster. And by knowing all this information, we can put this together with our projections that we have for the number of clusters of a given mass in a given distance to get the cosmology. And if it was just that, we are all set. But as I mentioned to you, we have systematic errors in our measurements that we need to take into account. And we need to perform these measurements with great precision to be able to distinguish between the different cosmological models with precision and accuracy. And we are working on that. We are developing the Y3 cluster cosmology analysis from DS data. And we expect to have these new results by this summer. So stay tuned. And I hope you have learned something about galaxy clusters. And I think they are very beautiful objects, of course. And if you don't want to go into details, but just learn a bit more, you can just follow me on Twitter. Time to time, I just present some information about galaxy clusters there in a very funny way. It's more fun than a presentation, I swear. And that's it. So thank you for your attention, and I'll be happy to answer any question that you might have.
Thank you very much, Maria, for that fascinating, informative, and very clear presentation and all that information. We had over 150 viewers for your lecture, which is very exciting for us. And there are a number of questions. The first question actually comes from Levi. Levi is going to turn 10 next month, and he's really looking forward to this lecture and is fascinated by the field. And he has a hard question for you, which is he'd like to know more and get a better idea about S8, what that means, what's the physical meaning of that quantity that has so much impact and is so important to you, and also where he can learn more.
Okay. Yeah, so S8, you can think about this quantity as something that measures how the galaxy and the galaxy clusters, how the matter in the universe get together. So we know that everything that has mass has gravity, and gravity is an attractive force. So things will, get together. But because the universe is expanding, right? It might happen that there is some force that are moving things apart, the galaxy and the galaxy clusters. So different models of the universe will give different predictions. They will tell how the galaxy in this expanding universe will behave, if they will be more clumpy in a given region of the sky, or if they will spread more in the sky. So the S8 just give us these like a way to know how is the fraction of this clumpiness of the universe, if they get more close or more far away from each other. So S8 just behave in the sense of controlling how these behave, at least in simulations, happen. Because we have the universe, the galaxy and the galaxy clusters, they are the way they are. We can just have a model and try to project how they are the way they are. And S8 is basically this quantity, like the physical meaning is just to measure the clumpiness of the matter in the universe.
So if we draw an analogy to the way people congregate now, imagine people in the diag in the middle of campus. So nowadays they'd all be 6 feet apart.
Yeah.
And in former times they'd be maybe in clumps having conversations and so on. So which one is a larger S8?
So now we are more far away from each other. So I would say that we are higher value of S8. So we are more spread.
Okay, cool. All right, so the next question, I'm not sure I really understand it, but the redshift of light from distant galaxies could be explained by something else. For example, time accelerating, or maybe physics changing over time, the fundamental constants changing. How are you able to rule out these possibilities, or can you?
Yeah, I mean, I know there are some exotic other models that explain or claim to explain that why there's no need for expansion, therefore there will not be this redshift. But one thing is that these models, they need to have projections that we can test, right? They can just not say, oh, I don't believe this is true because the timing or the dark matter behaves in a different way. So we need to prove that. And as far as I know, none of these more exotic theories right now are proving more things than the lambda CDM. And that's basically the thing behind. You have a theory, another theory that explains another way, but you need to explain what the Big Bang, lambda CDM, explains, but also you need to predict stuff. So we can say, yeah, you're right, your theory is right. It explains what you see.
So it's the best explanation. Next question. Does dark energy cause space to expand in the same way that the expansion of the universe is explained, or are galaxies pushed away from each other in a different way?
Again, I think it's very connected with the other one. It's something called different from dark energy that we don't know what it is, causing the things moving away from each other. I have to confess that I don't know what would be these other explanations. I know there are some, but no, I didn't read too much about them. But I mostly say that the things, they are going far away from each other. But for example, it might happen that they are coming together, right? Because of gravity. We know this is happening with Andromeda. Andromeda is falling towards the Milky Way. Eventually, they will merge because the gravitational force of the Milky Way and Andromeda, they are now interacting. So there is no way the expansion will be able to make they moving far away. So the only possible scenario is that they will just merge together. So they are not going far away from each other, but they are moving towards each other because the gravity.
Mm-hmm. Our viewers really loved the balloon demo, the expansion of the universe. That was Monica Wood, who's the head of our demo lab, who did that demonstration. And here's a question, which is, in that demo, not only did the wavelength get longer, but the amplitude got larger. So the amplitude represents something. So what actually happens to light?
Yeah, so that was just one analogy, right? But I also get confused because the wavelength is proportional to the inverse of the frequency. I think more about frequency, like the frequency get higher, then the wavelength get lower, right? And the frequency would be the pitch, which I would understand like as the amplitude, right? So I think I don't remember well the question, but so one thing happens to the frequency, inverse thing happened to the wavelength. So they are kind of related. And I think in that demo, what we want to basically show is that we start with the one wavelength that was this big, and as the space expand, it grow up this big, right? And this difference is just due to the universe expand itself. It's not that the galaxies are moving away from each other in a movement, in a proper movement, but they are just following the universe. Yeah.
So if you were to describe the amount of energy in a given volume in the universe, that would be decreasing with time as the universe expands.
Yeah.
Yeah. And that's inversely proportional to the wavelength, say, of a photon. Okay. And dark energy is mysterious to all of us. And maybe you could explain a little more why this may not be the right description, to think of it in terms of particles that are pushing.
Dark energy?
Yeah.
Really?
What's causing the pressure? Yeah.
I really don't know. Like dark matter, we can see that many people believe that it's some kind of exotic particle that we are trying to detect here on Earth with different experiments. So far, the results are not good. We do not detect dark matter, right? But for dark energy, I don't know. I really don't know what could be. If I knew it, I would be work on that to get my Nobel Prize.
But we do know that it does not attract matter the way dark matter does gravitationally.
No, yeah, it's exactly the contrary. It has a repulsive force, right?
So it's not made up of something that has mass the way we think of it.
Yeah, exactly.
Yeah. Another question. This is an interesting one, particularly since last week we had this amazing event of the rover landing on Mars. So the question is, if you sent some probe out or maybe something on the moon and look back at the Earth, would you be able to determine the mass of the Earth from lensing?
Okay, so if you put something on the moon and look.
Yeah, so if you were observing from the moon, some kind of sensor on the moon, put your telescope on the moon and looked at distant galaxies behind the Earth or some light source behind the Earth.
Yeah, like the problem here is that look to stars, but you are just really really close to our star, the sun. So you just imagine the sun here, and you are just a small star passing around the sun. And also there is something about distance. We will not see, you need to be to a certain distance to get the lensing to be more effective. But one thing that's interesting is that this other effect that did not study that much, but it's called microlensing, because not only we change the shape, but also the brightness of the background galaxy. And one thing that happens that we are here, and these people do, we are here on Earth, and we look to stars in the Milky Way, and there are other stars in the Milky Way more far away than the one that you pick up. And it might be that there is a planet that, like Earth, is around the sun. There are some other planet that is around this star. And the presence of this planet around this star will change the light curve that you see from the star that we are looking to. And this change, we will see like you have a light that goes like this, and we will see a peak, very characteristic peak in the light. So we say that, oh, something passed around this star. That might be a planet. And that's why some people use lensing, not weak or strong, but micro lensing to identify planets.
Great. My co-organizer, Roy Clark, has a question, which is about the gravity wave telescopes, so LIGO and maybe future ones like LISA. How do they contribute, these data contribute to understanding galaxy clusters?
Very good question. I think it's the contrary. Like surveys like DIAS and in the future LSST and others will help together with the detection from LIGO. We will help each other to get the expansion rate of the universe. For example, H0, right? Now we have measurements from CMB and measurements from strong lensing, time delays, and local universe, supernova and Cepheids. But there are some problems with those measurements because we need to define a referential frame going to different layers of distance, and then you add more and more uncertainties in your measurements. And one thing that gravitational waves could help to do is it's a different way to measure the Hubble constant. And I'll explain why. When we have a collision of two neutron stars, so then we have gravitational wave and LIGO detect that wave. So LIGO know the distance that that event happened, that the merge of those objects. So LIGO know the distance. But what we can do is to point all telescopes to that direction and try to see the light of this collision, right? So if you see the light, we will be able to identify exactly which galaxy that event happened. So if you can identify that host galaxy, we can have the redshift information. So then from LIGO, we have the redshift and from the distance, and from the or the survey, we get the redshift. We have the velocity. I show in some of my graphs, there is this relation between the redshift and velocity. And this is the Hubble relation, right? And then you can just plug these two numbers together in this equation. Velocity is proportional to some constant, and the distance. And this is the Hubble law, the way that we can estimate the H0 measurements. And we have done that, in fact. There are some articles that did this measurement with DIAS data and LIGO data. But the thing is that we just have one merge, right? And the uncertainties are really, really big right now. So you see the H0 measurements that show they are nice, they have a value and just a small error. Right now with gravitational waves, you have gigantic errors. So for the future, I hope they solve this question, the Hubble tension this decade. But if they don't, with LIGO and other gravitational wave detectors, we will have more and more neutron stars detections, gravitational wave detections. So we will increase our sample, therefore we will decrease our measurements. And it's a totally independent way to get H0 from the ways that we have now. So that's why I'm a bit excited about the gravitational waves and the use of this information with galaxies and perhaps galaxy clusters. Maybe we can find the correlation. Maybe this kind of event, this merger, happened more in this kind of galaxy clusters, for example. So we can also be able to make a connection with astrophysics. So yeah, I'm very excited about that.
Great. We have two more questions. Back to dark energy. I think our viewers are still struggling to understand a little about this. And there's a question that draws an analogy to light pressure and wonders if the name energy is given to this because of that analogy, or is there another reason that it's called dark energy?
Yeah, I mean, I know energy, you know, that equation from Einstein, it's proportional to mass square. That's why, you know, you don't feel when I show that pizza plot and I put together with dark matter, conventional matter, and dark energy, okay, and then you can think, okay, energy is related to matter. So that's why I put these things together, right? But I think the question was more like
in what sense is it energy?
I think I would say it's more like I think I don't know how to say it, to write down this very well. It's because it's like this repulsive force that we see, right? And you can make some connection with, you know, being a force, and then have some kind of energy associated to it.
So if the galaxies are speeding up their energy source, there must be an energy source. Is that what it is?
But you mean that if they are speeding up? But this is, I mean, this is a effect from gravity. Is not.
Let's go to the last question, which is about your data set, I guess. So you rely on these clusters with the red, and you're using the red elliptical galaxies because understand them. Are there galaxy clusters that that don't include mostly red ellipticals, and can you make use of those?
I would love to see those.
Yeah.
Yeah, this is what we would call a blue cluster, right? Because the galaxy are mostly red, but we also have some blue galaxies. Blue galaxy you can think as galaxies that's still forming stars. So you would be able to see those if you go more like far away in redshift, like to higher redshift, because there you still have this star formation in the cluster, right? So you would have a larger fraction of blue galaxies making part of the cluster. And so far, we have not identified yet this kind of blue cluster, but it might be possible. I'll be happy to see this happen.
Okay, wonderful. Well, thank you again, Maria, for this fascinating, great lecture, and also for the discussion and fielding these questions from our viewers. Thanks everybody for tuning in. And our next lecture is in 2 weeks, and it's in fact me talking about the physics of basketball. So that will be a change of pace. We're looking forward to that. And I will be working with Monica and the demo lab to tell you about this topic. See you next time. Bye, everybody.